Hi, Peter.
Hey, Peter.
Welcome to the Sintex show.
Thank you very much. Thanks for having me.
I have called you because I was looking for an international expert in sustainability and in understanding scope 1, 2, 3 calculations, and because we have made at Sintex a preliminary study of carbon emission and carbon emission reduction potential for a stator based on soft magnetic composites. But I would like your eyes on these calculations before we start sharing it with everybody. But first, will you introduce yourself? Tell a little about your background and what you're doing on your daily business.
Yeah, sure. And again, thanks a lot for inviting me. It's super interesting to hear what you guys have going on at Sintex. A few words about myself. I'm the managing partner of the consultancy GM+Consult, where we support companies navigating the sustainability and ESG space. It can be anything from climate strategies to validation of calculations to identifying green technologies with a potential for impact and so on. And this is, of course, something which is super important at the moment, considering the let's say the state of the planet, if I can put it like that. My background is that I have been working with the sustainability area for 1.5 decades nearly, and in an international context with Grundfos, who is a pump manufacturer and who has been very, very progressive in terms of the sustainability agenda in general. So I hope that I can bring some of those experience and perspectives into this discussion here. So again, thanks for having me.
Thank you. I'll just share my screen and then I'll show the calculations we have made. And please feel free to comment or if you find some holes, point them out because we still need to improve. So this is the first guess or first draft.
Sure, I have sharpened my pen here, and I will take extensive notes as you present the case.
Do you see my page now?
Yes, I do.
Okay, then I'll just scroll down, and here we have the latest news. We have made a little blog about the sustainable choice for soft magnetic composite stator designs.
Mm-hmm.
If you look at we made a simulation on a specific stator. It's around 200 to 300 watt motor, and here the original stator had a weight of 242 grams, and by introducing 3D designs, as you can with the SMC, we were able to reduce the weight to 203 grams. And when looking at what are the carbon emissions on the raw material supplies, on a traditional laminated stator material, the carbon emission we found from World Steel Association, an emission on 2.193 kilo carbon CO2 per kilo material produced. And when asking our suppliers and looking into their green budget, we found a number of, when making SMC raw material, of 0.95 kilograms CO2 per kilo material. So combining these, we were able to reduce 63% of the carbon emission on a stator. But that's
so
not the
Peter,
only.
before you continue, just let me make sure that I understand correctly here. So the traditional way, if we can put it like that, of producing a stator, that would be basically from laminated steel, and so that is the one option that we are comparing to the alternative, which is the SMC produced stator. Is that correct?
Yes.
Cool. Yes, got it.
Yeah. But then if we look at a specific case, a customer using 500,000 stators per year, that will give a standard or an emission of 265 tons per year with the traditional way of manufacturing. If you instead went into an SMC solution, you'll have a reduction down to 96 ton per year. So it will be a total of 169 almost tons reduced per year if you make this change.
Based on 500,000 units, right?
Yes. Yeah.
Yes.
Mm.
All right. Cool. So just to again, just to clarify here, a bit. So we are looking at these two technology options: laminated steel versus SMC. And what is the scope here when we are making the comparison? Is that from cradle, from mining to gate, or what is the scope that we're comparing here?
Yeah, I do not have values on the internal production carbon emission cost. So this only covers raw material. So this is from mine to our gate. It's not what happens inside our house. Because if you take lamination, then you have to cut away material to shape the geometry, and so to punch and to stack them will cost some energy, and the waste you produce will also have a carbon emission effect. But this is very strongly depending on the geometry. So this is from case to case. So therefore, I have not included that. The same with producing SMC. It's the cost to our gate. So I have not calculated on the cost of compacting the powder or to heat treat the parts afterwards. You could say the difference is that with SMC, we have a very high yield factor. There's no waste as you have when you stamp out lamination. But in SMC case, you have to heat treat it in a furnace at an elevated temperature. And I think that costs a little more. So I've made the assumption that the waste you have from lamination equals out the extra cost you have on the heat treatment.
Okay. So whatever differences there might be in the manufacturing processes, that's not included, and you try to make some fair assumptions that you have some losses and stuff when working with laminated steel, whereas when working with SMC you have a higher energy consumption for heating purposes. Yeah. All right.
So of course, next step on this will be to make a specific calculation on a specific component, and not just take this as a 500,000 parts estimation. But that'll be next step.
Makes sense.
But I'm glad you found the hole.
No, but I guess that's also why you invited me, right? I just need to understand the context here and so on. But I must say that from the graph on the top of the screen there, was it 63 or 64% reduction? That's significant.
Yeah. But that's not the only saving we can find here, because when we make these new designs of the stator, a stator is a piece of steel where you have on the inside you have the place where you deliver the torque, and then you have the yoke on the outside, and in between you have what we could call the bridge.
Mm-hmm.
And around the bridge, that's the place where you typically put your winding.
Mm-hmm.
But when working with three-dimensional properties, as we do when making SMC, we're able to reduce the height of that bridge. We can reduce it as far as the saturation level, the magnetic saturation level in the bridge is not going too high. So we made a simulation on a motor where we were able to reduce the height with about 30%.
Mm-hmm.
And when doing that, we could also round it, because when you wind on something that is square, it's impossible to wind totally squared. It's easier to wind round. So we designed the bridge with rounded edges, so the winding would fit better around it. And by doing that, we were able to reduce the length of the wire or the weight of the wire with 30%, but still remaining the same property of the motor. And 30%, my initial thought was 30% copper reduction. Copper is absolutely the most expensive part of a stator. So a reduction of 30% would be a no-brainer cost-wise. But then we looked into what are the carbon emissions based on copper production. And we found that the German Copper Institute had values of copper wire on 4.3 ton carbon emissions per ton copper wire produced. So it's about double up compared to what we just saw with lamination. And when reducing that amount with 30% linearly, you can see we could go from 172 grams copper down to 116. Then we could reduce the copper savings 33%. Taking that together with the one we saw before, that is, you can see here, the number is about 116 tons, just a reduction coming from copper. So in total, you can add that to the 169 we saw before. So therefore, 500,000 motors of this kind transferred from lamination to SMC will give a total reduction on 285 tons per year.
Cool.
And,
it sounds
here
super
again,
interesting. Sounds super interesting, Peter. Super interesting. I think my my first reflections here when seeing these numbers and also your approach, if I can comment a bit on that, that is, so first of all, I think that's a significant amount of CO2 savings, for sure. 63% reduction on the steel versus the SMC, and also a 33% reduction from the CO2 emissions from copper. I mean, that's quite some huge gains from switching to this technology. I also think that you made it quite clear that the scope is from the mine and until the gate. So whatever differences there might be inside the manufacturing processes, and I guess also post manufacturing, so to speak, when it enters the use phase, that's outside the scope of this study here, so to speak. So, but I think that makes sense from the perspective that as long as we are comparing apples and apples, or at least the same parts of the apples, then we get comparable numbers. And also, when we are talking about CO2 savings, very general, what you will typically see is that the largest chunks of the impact is actually related to the processes that are going on from the mine until the manufacturing process. So what you would call upstream scope 3. So you're hitting, let's say, you're hitting the target in the sense that you are addressing the largest climate impacts in general. So that makes a lot of sense.
I agree on that, because if we look at this number we got on carbon emission on lamination, this 2.193 kilo per CO2 per kilo steel manufactured. I have seen numbers for finished products, so including manufacturing, stamping, scrap handling, and so on, increasing that number to 2.4. So it's not a lot. So you could say the majority, at least 80% of the emissions are in the scope 3 phase.
Yeah, upstream. Agree. Yes. Agree on that. And that is what you typically will see within manufacturing, where you are producing physical products based on electronics, metals, etc., etc. So that makes a lot of sense. You also asked me to see if I could, in the introduction, you asked me so where are some of the perhaps not weak spots, but the spots that could, where maybe further analysis could be valuable.
Yeah.
If I understood correctly, then when you're making this comparison, you are basically, so you're comparing two different type of technologies, and the traditional, let's say, option, it's based on industry averages for steel and for copper, and then you're comparing that with a product specific values that you have obtained from your supplier.
Yes.
I think that is typically how you would go about it in the let's say in the initial phases of this. But of course, an industry average can basically cover a large difference in span, if that's the right way to put it. So depending on whether or not the steel is produced using I don't know what hydro power somewhere, or it could even be nuclear or whatever, something with a very low CO2 factor embedded in that energy source can be completely different compared to if you are then talking about steel being produced in a part of the world where the energy source is brown, based on coal or whatever it might be in that.
Mm-hmm.
So in that sense, I think it a suggestion maybe from my side would for further analysis down the road would then be to actually see if you could get more specific numbers, if that's the right way to phrase it, for a specific steel type produced at a specific location from a specific supplier, right?
Mm-hmm.
Because then you would actually end up with super comparable figures, and perhaps, and now I'm just thoughts are flying around my head here, because you might also be able to identify the thresholds, so to speak, where you say, okay, under the circumstances where the steel is produced on hydropower or nuclear, whatever, then the CO2 savings would be less. But when you are then sourcing from another part of the world where the energy source for the steel production is based on coal or whatever, then it would be different savings, of course. So I think it makes sense when you are talking about when you're trying to evaluate two technologies up against each other. What you've done here makes total sense, given where you are in the process. And then at a later stage, when a customer asks for what are the specific CO2 savings here, okay, then you probably need to compare product to product in order to have a valid base for comparison. So that could be a suggestion for next step. Another thing here I would also mention. Now you set the scene very clear here when you said talking about CO2 reductions, and obviously, given the situation we are in with the climate and climate change already affecting us today, it makes a hell of a lot of sense to have that focus. But there are, of course, also other sustainability dimensions that could be worth investigating, if I can put it like that. So we tend to have a very one-dimensional focus for CO2, and that makes sense because it's a critical problem that we're facing. Of course, we also have issues around biodiversity, what is the water impact of the mining operations, so on and so on. So there are, and you could even extend that to some of the social dimensions as well. So there is definitely a possibility to nuance and broaden the scope. What are the different elements within sustainability, if I can put it like that, that you want to compare. But again, this does not mean that what you have here is not good and makes sense. It's just more, suggestions for how to move ahead as you go forward with this technology.
We have thought about potential afterlife of these kind of stators, because we have seen that traditional motors that are winded on lamination can be very difficult to disassemble
Mm-hmm.
and take the iron and separate it from the copper. So very often motors end as they are as scrap going into steel production. So you lose the copper, and in fact you pollute the steel with the copper, so makes a lower quality of steel. But in an SMC stator, as SMC is more fragile than laminated, you could put this into a jaw crusher and just powderize the stator material. So you take the iron powder out, and you have the copper as a pure material that can be recycled.
That is super interesting, right? Because I mean, now we're starting to talk about circular principles and circular economy, and the possibility of reusing the raw materials, keep them in a loop, and reusing them over and over again, and that for sure is part of the solution to the multiple sustainability challenges that we are facing. So if you have a design here which makes disassembly and reuse in a small loop much more feasible, then I think you're onto something here, which is really, really interesting. That's for sure, and that obviously has a tremendous not only climate effect but also effect on multiple other sustainability dimensions as well. Yeah. Very interesting, Peter. Maybe just one final comment here from my side. I like the calculations here that you have made. I think maybe it's more meant as a sort of a bow tie or whatever it's called on some of the suggestions that I made the last couple of minutes. If you want the let's say if you want the facts, then I think, you know, going into the area of making detailed LCA calculations on this would definitely be the way forward, which I would recommend for you. Also, there you will capture some of these steps in the value chain that has perhaps not been included as of now, but both we talked about some of the negative impacts from the manufacturing processes, but definitely also the gains when we are talking about end of life and the possibility for reuse of the raw material. So so that would definitely be the way forward that I would recommend for you guys.
Yeah, thank you. We are already in dialogue with a local Danish university on making projects on LCA calculations on these stator designs. So hopefully within the next half year, I'll call back and show you those data.
I would love to. I heard a good expression many years ago, and I think today it's more valid than ever, and that is cut the fluff, show me an LCA. I think that's a very, very good expression for what it is that we need to do when we're trying to make these calculations here. So feel free to invite me for further dialogue on this. I would be super curious to see what does that look like, and does that confirm your initial calculations here.
Yeah. Thank you very much, Peter.
Thank you for having me, and have a great day. Thanks for the enlightening discussion here.
Thank you. See you.
Thank you. Bye.
Bye.